Okay, in this video we're going to discover or learn how to write any decimal as a fraction. Okay, so let's just start with something really easy. 0.5. Now 0.5 can be written as a fraction, and we know what that fraction is. That fraction is 1/2. But how would we arrive at that if we were not aware that this fraction was 1/2 just by looking at it? Well, here's the process for finding it. Multiply this decimal by a number or a power of 10 such that the decimal will move to the left, or to the right rather, of the number itself. Okay, so this is for non-repeating decimals. We'll move this, we want to move that decimal right there. Now, the way we would do that is by multiplying 0.5 times 10. And what we end up with is 5. Okay, so now we write 5 over the number that we multiplied by in order to get that decimal on the right side of the number, which that number was 10. And so what we can do now is write this out as a prime factorization. Say 5 times, and then over 2 times 5. Okay? So these are the prime factorizations of both of these numbers, 5 and 10. 5 is a prime number, 2 is a prime number, and 5 is a prime number. So these 5s cancel out now, leaving, there's nothing up top, there's actually a 1 there that we didn't write. We actually have 1 over whatever is left, 2. Okay, so there's 1/2. Now let's do it again for a number that we know what the answer is already. So let's take 0.125, which we know is 1/8. And let's see how we're going to figure this out. So how many, I want to get this decimal to be over here. What would I multiply 0.125 by to get it to be 125? Well, I would, pardon me, I would multiply by 1,000. So I'd take 0.125 times 1,000, and that would give me 125 over 1,000. Okay, so now we do the same thing again. We write out the prime factorization of 125 and of 1,000. Well, we got to figure out the prime factorization of 125. So what we'll do is we'll take 125 and divide by 5. Okay, so 5 goes into 12 2 times. 2 times 5 is 10, right? So we subtract that out, there's 2 left, bring down the 5, 25, 5 goes into 25 5 times. So we have the 5 times 25. We can write this as a tree if you're more comfortable with that. 125, okay, here's 1 5 here, and then we had 25 right here. If I want, this isn't a prime number yet. 25 can be broken down into 5 times 5. So these are all prime numbers. 5, 5, and 5 are prime numbers. So I could write this numerator, instead of writing 125, I could write 5 times 5 times 5. All right. Now how about 1,000? Let's break 1,000 down. 1,000 can be rewritten in the tree form as 2 multiplied times something. What times 2 equals 1,000? Well, it's 500. Okay, and 500 can be written as 5 times 100. And 100 can be written as 2 times 50. And 50 can be written as 5 times 10. And 10 can be written as 2 times 5. I wrote so fast it wrote right off the page. All right, so we can kind of gather these terms together like this. We have a 2 times a 5 times a 2 times a 5 times a 2 times a 5. It might be helpful to rearrange these so that the 2's are together and the 5's are together. So I have 2 times 2 times 2 times 5 times 5 times 5. Okay, and now I can write that right here. This prime factorization of 1,000 can be written underneath. We can actually rearrange these so we have 5 times 5 times 5 times 2 times 2 times 2. Okay? And the 5's will cancel out, and you're left with, again, 1 over 2 times 2 times 2. Now, 2 times 2 is 4, and 4 times 2 is 8, so you're left with 1 over 8. Now, this works, this method of factoring by primes and then setting them in the numerator and denominator and crossing out those that cancel. It turns out that works for any number that doesn't repeat, but that terminates. So I'm clear what I'm talking about here. I'm not talking about irrational numbers. I'm not talking about the transcendentals. I'm talking about simple decimals that terminate. So what we want to do now is look at one that isn't obvious, that we wouldn't necessarily know off the top of our head. And let me see if I can find one. Okay, here's one. Let's take, well, let's get a new piece of paper here. Let's take this decimal here, 0.096. Now this may appear clean or clear as a fraction to some of you, but if you didn't know how to do this, you would just follow the same process. You would multiply by some power of 10 such that the decimal would be over here, and that power of 10 would be 10 to the power of 3 or 1,000. So you'd multiply 0.096 times 1,000, and what that would give you is it would give you 96. Okay, now the thing to do is to divide 96 by 1,000. And we're going to do the same thing we did before. Let's factor to primes 96. Okay, now it looks like we can plug a 3 in there. So if I divide 96 by 3, I get 3. 3 times 3 is 9. 9 minus 9 is 0. Bring down the 6. 3 goes into 6 2 times. So if I'm factoring with this tree 96 by divide by 3, you end up with 32. Okay, 32 can be, this is 4 times 8 4 can be prime factored as 2 times 2, and 8 can be factored as 2 times 4, and 4 can be factored as 2 times 2. So you end up with this prime number, 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 and this prime number. Okay, so we have here the prime factorization of 96 as 3 times 2 times 2 times 2 times 2 times 2. All right, so we'll write that up here. Three times 2 times 2 times 2 times 2 times 2. Okay, now we'll do the prime factorization of 1000, which we just did. It's going to be the same, 5, 5, 5, 2, 2, 2. So we could say 5 times 5 times 5 times 2 times 2 times 2. And cross out the things that are shared in both the numerator and denominator. So in this case would be these 2's and nothing else. So now let's write down what's left. 3 times 2 times 2 over 5 times 5 times 5. What do we get? 3 times 2 is 6, times 2 is 12. I get 12. And then in the denominator, I have 5 times 5 times 5. 5 times 5 is 25. 25 times 5 is 125. And it turns out that that is, in fact, if you divide 12 by 125, you get 0.096. Okay, that terminates nicely. So this is a rational expression that it ends in a nice terminating decimal. Okay, so what about decimals that don't work out like that? Flip to a new sheet of paper, and let's start again with a number, this time a number that repeats, that we know the solution to. So let's take the first easy one, which is 0.3 repeating. Okay, we know that 0.3 repeating is equal to 1/3. We know that, but let's now find it using some kind of system that will take us from a repeating decimal to a fraction. And here's how that works. So it's very similar to what we just did, with one important exception. Take 0.3 and multiply it by 10 to the power of whatever number is necessary to move this decimal over to the right of the repeating number. And we'll see that as the numbers repeat more and more, you'll have to do this again and again with bigger powers of 10. But right now we just need, okay, 0.3 times what equals 3? Well, 0.3 times 10, so we'll say 0.3 times 10 equals 3. So now what we do, this is the only difference, it's where it gets a little bit complicated, is we say, okay, 10 minus 1. I don't know why I wrote minus 9. I think I was thinking of the answer to 10 minus 1 in my head. So 10 minus 1. So in other words, 1 less than whatever you had to multiply by 0.3 to get to 3. Just roll with me on this and you'll see how this works. So now that's 3 divided by 9. Now, you might already be thinking, let's reduce, but find the prime factorization of 9, which in this case is just 3 times 3, okay, and rewrite your fraction here as 3, which is the prime factorization of 3, over 3 times 3. cancel out what can be canceled out, and what you're left with is 1/3. Now, I quite honestly not thought about it that way before, but it's kind of interesting that it works out. Let's try another one. Let's try 0.6. Okay, 0.6 repeating, we know, is going to be 2/3. We know that, but can we prove it? Okay, that's a different story. Can we prove it using some application of this gizmo up here? Let's try that. So I'll take the same analysis. I got 0.6 and I want to know, what do I have to multiply 0.6 by to get 6? Well, I have to multiply it by 10, so 0.6 times 10 equals 6. So I'm going to divide 6 by 10 minus 1, which is going to be 6 divided by 9. Well, I'm going to write down the prime factors of 6 and 9. Since these are small numbers, I'll just write it out here. That's 2 times 3, and then 3 times 3 times, well, 3 times 3 to get to 9. Okay, now cross out the numbers that exist on both the top and the bottom, and you're left with just 2/3. Okay, now just like we did in the last problem, let's apply this system to a repeating decimal whose answer we don't already know to test the theory. And we'll just choose one at random. Let's choose 0.12, 12, 12, okay, repeating on forever like that. You could imagine this number existing somewhere, and so you could write this as 0.12 repeating. Okay, so how do we solve this as a fraction? Well, what number do we need to multiply 0.12 by to move the decimal point to the right of the 2? We would need to multiply 0.12 by 100. Right, and that would equal 12 divided by, remember we're going to subtract 1 from whatever that is. So 100 minus 1. This gives me 12 divided by 99. Now I need to get really good with my prime factorization of these 99, 999, 9,999, etc. So first let's prime factor 12. 12 is easily prime factored as 3 times 4, and 4 is prime factored as 2 times 2. So 12 can be rewritten as 3 times 2 times 2. Okay? Now how about 99? 99 is a bit of a different bird. Let's take 99 and divide something we know we can divide into it, like 3. And we get 33. So if I take 99 and I write it out with my tree, I'll have 99, and that can be written as 3 times 33. 33 can be rewritten as 3 times 11. So the prime factorization of 99 is 3 times 3 times 11. Cross out what exists on both the top and the bottom. Okay, I can cross out 1 3's there. And so let's rewrite what's left. We have 2 times 2 over 3 times 11. Well, what's 2 times 2? That's 4. What's 3 times 11? 33. 4 over 33. Does 4 over 33 equal 0.12 repeating? 4 divided by 33 equals 0.12 repeating. So that works. Let's do another one. This is kind of fun. Okay, so let's take another one with a little bit more complexity to it, just to stretch our imaginations. How about 0.3 3, 6, 7, repeating. Okay, so 0.367 is going to repeat. Now I have no idea what this is going to be, but we'll just follow the same process. That is, I'm going to multiply 0.367 by some number that gives me 367 by itself. Well, that would be multiply it times 1,000. So what I'll do is I'll write 367 over 1,000 minus 1. So that's 367 over 999. What is the prime factorization of 367? It might be prime, I don't know. 367. Yeah, that might actually be prime. Let me double check. Okay, so 367 is a prime number. So in this case, that's going to be the most reduced answer because 367 was prime. Okay, bad example. Let's find another one. Here's one that won't be prime. If 0.367 is prime, 0.368 will definitely not be prime because it's an even number. All right, let's start over. Say, well, I'm going to have to multiply this times 1,000 to get the period right there, the decimal point to the right of the number. This is 0.368 repeating. So now I have 368 over 1,000 minus 1. Okay, well that's going to equal 368 divided by 999. Well, what's the prime factorization of 368? Well, I don't know, but I know I can divide this by 2. So I'll take the easy route and divide by 2. Okay. $184. All right, so I've got 368, and I have 2 here and 184 here. Well, again, I don't know what 184 is as a prime factor, so I can take 184 and again divide by 2, and that gives me 8, 16, 2 goes into 24, 12 times. What did I do wrong? 2, 16, 24. Oh, dummy. 9 times 2 is 18. I don't know what I was thinking. So that 2 goes into 4 2 times, so I have 92. 2 times 92. I don't know what I was thinking back there. Now I have 92. Well, what does 92 factor into? 92 divided by 2. Okay, 2 goes into 9 4 times. 4 times 2 is 8. 9 minus 8 is 1. Bring down the 2 for 12. 2 goes into 12 6 times. So I now have 2 times 46. Okay, well, now I can start doing this in my head because I know that 23 times 2 is 46. 23 is a prime number, so I can stop right there. So the prime factorization of 368 is 2 times 2 times 2 times 2 times 23. Okay, so let's go up here and write that. 1, 2, 3, 4. Yeah. Okay, so this equals 2 times 2 times 2 times 2 times 23. All right, now on the bottom we have 999. Well, what is the prime factorization of 999? Okay, so we'll just start again. We can do this one kind of in our heads. That would be 3 times 111. Right? That's 333 times, yeah. So 3 times 3 times 3 times 111. Okay, that's the prime factorization of 999, because 111 is a prime number. Yep, just confirming that it is. So I'll write up here 3 times 3 times 111. Okay, now let's cross out what can be crossed out. Nothing. Okay, so this appears to be simplified as 368 by 999. Let's see if that's what it is. .368. Okay, so let's find another one. Hopefully we'll find one that works out to be something a little bit different than that number over 999. Let's try how about 369 repeating? This might be interesting. So 0.369 repeating. Well, we're going to multiply again by 1,000. And then that will give me 369. We'll divide by 1,000 minus 1, which is 999. Now it's the fun game of prime factor. 369 can be divided by 9. Okay, 9 goes into 36 4 times, and it divides out cleanly. Okay, and 9 goes into 9 once. So 369 can be factored as 3 times 3, which is 9, times 41, which is prime. Okay, so this will equal 3 times 3 times 41. And then in the denominator, what does 999 factor out to? Well, let's do it again. 999 is equal to if I were to divide by 3, I would get 3 times 3, 33. And then here I could say, well, divide by 3 again, I'll get 3 times 111. So this is 3 times 3 times 111. Oh, good. We have something interesting happening. The numerator contains a 3 and a 3, and so does the denominator. So I could rewrite this as 41 over 111. Okay, and does that work out to be 0.369 repeating? 41 divided by 111. Yep, works out to 0.369 repeating. So that's fun. Now here's a question. How do I write 2.369 repeating as an improper fraction? This is where this actually gets useful. Now remember, we found that just this part right here is equal to 41 over 111. Okay, so that is actually added to 2. Well, now we can find a common denominator where we're going to multiply both the numerator and denominator here, which is 1, by 111. Okay, and what we get is 222 over 111 plus 41 over 111. And what does that equal? Well, 222 plus 41 is equal to 3, 6, and 263 over 111. And since 111 is prime and none of its multiples are 263, we know that this is the final form, the improper fraction. This is equal to 2.369 repeating. Don't believe me? Take 263 divided by 111, and you'll get the repeating decimal with the whole number off to the side. Let's do this one more time. Let's find 5, and then we'll say let's do 58 repeating. Okay, 5.58 repeating as an improper fraction. For just the time being, let's leave this guy alone. We're going to leave the 5 by himself, and let's just focus in on this 0.58 repeating. So we have 0.58 repeating. I want to know, what do I multiply 0.58 by to get the decimal over to the right side of the 8? And that would be by 100. Okay, so I multiply 0.58 times 100 and I get 58. Now what I'll do is divide 58 by 1 less than what I multiplied it by. So that would be 99. And then we'll do our prime factorization. 58, okay, I don't know what it can be divided by, but let's try 2. 2 goes into 5 2 times. 2 times 2 is 4. Okay, and 5 minus 4 is 1. Bring down the 8. 2 goes into 18 9 times. 29 is prime. So the prime factorization of 58 is 2 times 29. Okay, so that equals 2 times 29. And remember, the prime factorization of 99, let's just do that, 99, that's 3 times 33 which itself is 3 times 11. So 3, 3, 11. 3 times 3 times 11. Well, none of these cancel out, so we're left with 58 over 99. Okay, remember, we have to add this part. We have to add this part to our 5 from before. Okay, that needs to be added. So we have to find a common denominator. Well, we're going to multiply 5 times 99. Okay. $495 over 5. Or rather, 495 over 99. Okay, so this is going to equal 58 over 99, and that was the repeating decimal part of our calculation, plus 495 over 99. I'll just double check that. 495 divided by 99. Okay, good. All right, so now we will add 495 to 58, and 5 plus 8 is 13, 9 plus 5 is 14, plus 1 is 15, and 4 plus 5. So I now have 553 over 99. Okay, let's do this again. Just try to find, just happen across some numbers that work out nicely. Okay, so let's do this one. Let's say we're given the number 6.1248, where 1248 is a repeating decimal, and we're asked to write this as an improper fraction. Okay, so we have to ask ourselves a simple question. Remember, we're going to take this guy, the 6, and we're going to sequester him off for just a minute. We're going to focus on just this number, just this decimal, 0.1248 repeating. Okay, what do we need to multiply 0.1248 by to get the decimal point to the right of the 8? Well, the answer is 10,000, right? Because if we multiply by 10, 100, 1,000, 10,000. So we'll multiply by 10,000, and that will give me 1,248. Remember, I'm going to divide by 1 less than the total number I had to multiply by, so that would give me 9,999. Okay, so we need to do the prime factorization of both of these numbers. Alright, so let's just say you did not know anything you could divide. Let's just think about this for a minute. Okay, 48, that can be done 12 times 4, okay, and 12 is 12. So I wonder if I can divide 1, 2, 4, 8. Let's see if we can divide this cleanly by 12. Okay, so I know you're supposed to divide by only by primes, but let's just see here. So I have here 12 goes into 12 one time. 1 times 12 is 12. Okay, yeah, this comes out to 0 and 48. 12 goes into 48 4 times. So I have 4 times 12 equals 48. Okay. So 104 times 12, let's double check that. 104 times 12 should equal 1,248. So 8, 1, 0, 0, and 2, okay, 4, 0, 1, okay, 8, 4, 2, 1, 1, 2, 4. It checks out. Okay, so here's what we can write down. I have 1, 2, 4, 8, and I want to find the prime factors of that. Well, 12 times 104. Okay, 12 can be prime factored as 2 and then 2 times 2. Oh, whoops. So that would be 2 times 6, which is 2 times 3. Okay, so 2, 2, and 3, 2 times 6. There's the prime factors of 12. How about the prime factors of 104? Well, let's see. 8. 8 should go into it. How about 104 divided by 8? Okay, that goes in once. And 24 goes in 3 times. So 13 times 8. 8 times 13. Well, 8 can be 2 times 4, and 4 is 2 times 2. So 13 is prime. So here's what I've got. The prime factors of 1,248 are 2, 2, 3, 2, 2, 2, and 13. All those are the prime factors of 1,248. So let's rewrite. In the numerator, all these in order. Maybe we should order them first. So I had a 2, a 2, and a 3, and then a 2, and a 2, and a 2, and then a 13. Okay, so I'm going to put 5 2's, and then a 3, and then a 13. Okay, so here's 2 times 2 times 2 times 2 times 2, 5 2's, then a 3, and then a 13. Let's make sure that that actually equals 1,248. 1 times, 2 times 2 times 2 times 2 times 2 times 3 times 13. 1,248. Okay. Now I want to factor 9, 9, 9, 9. Well, how do we do that? Okay, so this 9, 9, 9, 9. That is 1,111 times 9. 9 times 1,111. Okay, is 1,111 prime? Let's see. It can be divided by 11. Okay. So 1,111 can be divided by 11. And that would be 11 times 101. Now 9 can be broken down into 3 and 3. So the prime factorization of 9,999 is 3 times 3 times 11 times 101. So that's 3 times 3 times 11 times 101. The reason I wrote it like that was so we could see what would cancel, and this would cancel, just that 3. And so what we're left with here is 2 times 2 times 2 times 2 times 2 times 13 over 3 times 11 times 101. Okay, well, we can do this. What's 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 13. 32 times 13, 6, 9, 2, 3. Okay, 416 over 33. 3 times 11 times 101 is just 101 by 33. So we'll multiply this out. 3, 0, 3, 3, 0, 3, which just gives 3, 3, 3, 3. Okay, so 3, 3, 3, 3. So there is your fraction for 0.1248. That is the fraction in the most reduced form. And so remember, we still have to add in 6. Okay, so we need to multiply 6 by 3,333, which is, okay, that's 18, carry the 1, 18, 19, carry the 1, 18, 19, carry the 1, 18, 19. So 19,998, is that what that multiplies out to? Yeah. So what this equals, find some more space here, this is equal to 416 over 3,333 plus 19,998 over 3,333. Okay, so what does this equal as an improper fraction? Well, let's add it 416 to 19,998. 8 plus 6 is 14, carry the 1. 9 plus 1 is 10, plus 1 is 11. Carry the 1, 9 plus 4 is 13, plus 1 is 14, carry the 1, 9 plus 1 is 10, so 20,414. Okay, so this equals 20,414 over 3,333. Now let's double check that that actually equals 6.1248 repeating. 20,414 divided by 3,333. Yep, and it does in fact equal that repeating decimal. So this has been a run through of these various problems. If the decimal terminates and doesn't repeat, then you just divide by 10, 100, 1,000. If it repeats and you know what the repeating section is, you divide by 1 less than the number you multiplied by. That's really the trick. And then you have to find the prime factors, and sometimes that can be complicated. But once you know the prime factors, you write out the prime factors and then divide out the numbers that are shared on both the top and the bottom, and that gives you your most reduced fraction. So this is kind of a foolproof way for going back through all of our examples of finding the fraction